Good evening, everyone. Welcome to Science at the Theater's Just Say No to Carbon Emissions, sponsored by the Friends of Berkeley Lab and co-sponsored by the Berkeley Energy and Resources Collaborative. My name is Jeff Miller, and I'm Head of Public Affairs. Our topic tonight is clearly tied to the 40th anniversary of Earth Day, but for all of us at the lab, and I really do mean this sincerely, every day is Earth Day for us. As many of you know, Berkeley Lab is an international center of energy research with a very local flavor. Our scientists, many of whom are Berkeley and East Bay residents, grapple with such huge questions as how to reduce energy demand and increase efficiency, store and distribute energy more effectively, create new sources of renewable energy, improve combustion, and develop innovative materials that will make energy cheaper. So while the title of tonight's Science at the Theater is Just Say No, Berkeley Lab is really all about saying yes, and that's yes to basic science, yes to applied science, yes to policy analysis, yes to finding technological solutions and bringing them to the marketplace, and yes to restoring the planet's carbon balance, which is at the heart of the lab's Carbon Cycle 2.0 initiative. This is admittedly an ambitious, audacious, and some would say outrageously unattainable science agenda. We don't think so, and some of the reasons for our confidence will be showcased tonight. Our first speaker, Ramamoorthy Ramesh, will explain how we are trying to make solar energy more affordable. He will be followed by Nan Zhou, who I think will startle you with her largely untold story about how the lab has partnered with China to reduce that country's carbon emissions. Our final presenter will be Kurt Oldenburg, who will discuss how we might be able to safely store CO2 underground. Each speaker will have about 12 to 15 minutes to tell why their work matters to all of you. At the close of the presentations, all three who are seated here in front of me will take their seats on the stage for a question and answer period. So my question to you right now is, how many of you are attending Science at the Theater for the first time? Raise your hands, please. Okay. We have been experimenting with format, and for both the first-timers and the veterans, just so you know, we do have a question and answer period at the close. We're going to experiment tonight by actually taking the mics out of the stands and roaming. There'll be two of us, so you can stay seated. We'll pass the mics to you. Please keep your question short and your commentary shorter. We don't want to have to wrestle the mics from you. I'm sure there'll be lots of questions. I'm also supposed to tell you that there are fire exits here, and the way you came in is probably the best way to get out, but I've now satisfied my state of California requirement. Another thing we'd like you to do is to spend a moment and fill out your audience survey. Even if you've already done this at previous Science at the Theater gatherings, we evaluate each of the evenings separately. You can hand them back to one of our volunteers as you exit. We've also reproduced two of the presentation slides tonight because we think that you will find them useful. They're a little complicated, and you might want to study them or look at them when the presenters actually have them on screen. Lastly, we will be back on this stage in 2 weeks for another Science at the Theater in a different group of Berkeley Lab scientists. The topic on May 10th will be the House of the Future. So if you're wondering if we will all be living in hay bale houses with passive solar in the decades ahead, this will be your time to find out. So thank you for your attention. Ramesh is going to start us off, so please welcome Ramesh.
Thank you, Jeff. First of all, thank you very much for sharing your Monday evening with us. Thank you for supporting Berkeley Labs and University of California, Berkeley. It's a distinct honor to be here with my colleagues to give you our perspective on what this means to all of us. Okay, so my part has to do with the first question, which says, can I make solar energy very cheap? And I want to take you through some of the kind of the prelude to this whole problem by beginning with a very sobering video or a view graph. This is some measurements which has been going on for a while. For those of you who have heard Steve Chu or my other colleague Arun Majumdar, you might have seen this view graph from Steve's collections. Basically, it's measuring the area, approximate area of the polar ice cap as a function of time. And you can see it's shrinking and it's growing depending on the seasonal changes. But what's really interesting is what you will see here. right around a few years ago, maybe 3, 4, 5 years ago, there's a big drop in the area. And you can go back and say, you know what, this is all just fluctuations in the climatic patterns. Or you can take a more active view of this and say, something is really changing. And therefore, there's a big debate that's going on. And of course, part of the debate is the fact that one has a whole bunch of things that are happening around us. And so we can go back and say, let's take a more proactive look at this. And this brings us to the Tokyo subway map. I make a joke out of it. This looks very complicated, isn't it? So I want to walk you through every one of those stations, all the way from Shibuya to Tokyo Main Station and every other station in between. Okay, but this is a very important view graph. What it talks about is the balance of energy. What do we consume in terms of energy? That's on the left side. And you can see there are 3 big animals, 3 big gorillas. Coal, which is about 23%. By the way, all of these are in percentages. That's the total US consumption, which is about 100 quadrillion BTUs. Very large number. 10 to the 20th joules of energy being consumed on an annual basis. And you can see we consume about 23% of coal. First bad news. About 23% of natural gas. Second problem. And 40% of petroleum. Really big issue. And this has 2 very, very serious connotations to it. One is simply a scientific connotation, which is the amount of carbon dioxide we're putting into the atmosphere. That's the first part. The second part of this has very strong geopolitical connotations, which is something that we need to grapple with as a world, as a country, as a hemisphere. So if I add up all of these, the sources of our energy, 90% of that is coming from what we call fossil fuel. All of these are fossilized into the Earth's crust. Okay, if you look at the top part, that's even more sobering. Only about 10%, and out of which the particular topic I'm going to look at is solar. It's 0.006 on this chart. This is about 5 years old. So it's about 0.1%, approximately of that order. Very, very small fraction of our energy comes from solar. And therefore, there you say, oh my God, this is really a bad problem. But I say, this is a fantastic opportunity to go grab this market share. Okay, so that's one part of the whole story. On the right-hand side of this picture is an even more kind of a troubling picture. Let me take you through that. This is the consumption of energy. How do we use all of this 100 quads of energy? On this side, you have about 20%, 25% of transportation, all the cars, the airplanes, and the trucks that we drive, 25%. Industrial manufacturing, paper, steel, whatever else that we manufacture, takes about 25%, maybe 30% of the energy. The other part is buildings, and that's the focus 2 weeks from now. Buildings consume about 25-30% of the energy. Okay? But that's okay. We need to have all of these. These are all important components. But the big problem with all of this is this red box that I show here. We waste about 55% of this total energy. We throw it away. Every time you drive your car, you're exhausting gases at 600 degrees centigrade. And that's basically throwing energy out into the open. Every time a steel billet comes out, it comes out at 800 degrees centigrade. Every time a glass plate comes out of a manufacturing plant, it is coming out at high temperature, you're throwing out that energy. So if you listen to Steve Chu and Arun Majumdar, my other colleague, they will say the lowest hanging fruit is not here. The lowest hanging fruit is making our things more efficient. Let's make them use the existing energy in a better way. So you already get the picture. Energy is not a single animal. This is a multifaceted animal, which really brings us to the center of carbon capture 2. This is our mantra. This is the wagon that we're circling around, and it has many components to it. What I'm going to focus on briefly today is solar photovoltaics, how to use the power of the sun to get energy. But a corollary, a very important corollary to that is energy storage. I just can't grab the sun's energy, put it in my pocket. I have to do something with that. So storage of energy, battery technologies are very, very critical to this. Okay, artificial photosynthesis is another way of mimicking nature. Can we use the power that is invested in nature to probe artificial photosynthesis approaches? Biofuels is something that you must have heard of from Jay Kiesling, my colleague. And you will hear today from Kurt about carbon capture. Analysis of all of this, how does all of this happen, is a very key component as well. So when you start putting in energy as a picture, one needs multiple components. You also have to worry about the capture of the carbon dioxide that you're putting into the atmosphere. Okay, so let's now focus on the particular topic that I was going to discuss, which is basically capturing the power of the sun. And in reality, every one of us should be a billionaire because so much of energy coming out from the sun. Let me give you some numbers. The sun puts about 120,000 terawatts of power. And for us, we only need about 15 terawatts today worldwide. We need about 3 to 4 terawatts of power for the US of A. So the sun is very capable of making all of us very wealthy intellectually, financially, and energy-wise. The question is, why is that not happening? So let's take everybody through that. These different points on the world are points where there's a huge amount of solar intensity, very large amounts, about 350 watts per meter squared of average solar intensity. So the question that we have to ask is, why did this not happen soon enough? One obvious reason, and a very important reason, is the fact that solar energy is not cheap enough. And I come to this business from the semiconductor side of life, where there's only one important rule, which we all know, which is cost per bit. I will only pay the minimum cost to do one amount of transaction. In the energy business, that's exactly the same argument. It's the cost per kilowatt hour that the customer is willing to pay. So the question that we've been asking from the research point of view is, can I make solar energy dirt cheap? So let me take you through a cartoon. This is home. And what we want to do is to try to take a small slice out of this and ask the question, can I forget about doing any sophisticated manufacturing? Like we do currently with silicon-based, the stuff that you have on your rooftops is all based out of silicon, which is a very complicated process of creating these materials, putting it on a glass plate. What we would like to do is to instead take a piece of the cake and use it in as virgin a form. So in some sense, we're trying to mimic fossil fuels by using the material in the as mined form from the earth. So if you look at the chart, this is from the Geological Survey, you can see that silicon, of course, is a very popular element. Oxygen, of course, the most popular element. We know why. But silicon, 5,000 tons of it is manufactured in very high quality. Much of that goes to Intel, Applied Materials, Toshiba, Samsung, all of the semiconductor manufacturing people. So this is a very, very high value commodity. On the other hand, if you look in this chart, there are a lot of elements. Now, my favorite element, of course, is iron. It's a very primordial element. It's inside us. It was forming when stars were forming. So we can go back and look at all these mineral-type elements and ask the question, can I use it as a photovoltaic material? And so this brings me to one piece of data that I want to show you. And much of us know that Telegraph Avenue is a very interesting place. A lot of things can be obtained on Telegraph Avenue, but there's also a Rosie's bead and a mineral shop. And you go there, you can pick up a piece of malachite. I'm not sure if you could see, oh, that went too fast. If you could see the malachite in the background, that's a picture of a piece of malachite. I mean, sometimes people use malachite for jewelry or for decoration purposes. Malachite happens to be the primary source of copper, and copper is a very interesting material. Malachite is basically a carbonate of copper. So the experiments that we're doing, and this is really why you need a framework like Berkeley Labs, where physicists and chemists and engineers can all come together to try to solve these very complicated problems. So we use a piece of malachite. And if you look at these curves, these are basically the most important curve that you would like to have in terms of using the material as a solar cell. What we're comparing here is a synthetic material, copper oxide, and looking at its performance, comparing it to a naturally occurring material. There's virtually no difference between these two systems. Have we solved all the problems? Absolutely not. But we are on a track to look at a very interesting alternative approach to silicon or very expensive materials by looking at minerals. as a source of photovoltaic energy conversion. The argument here is that now I can start to look at this whole process of photovoltaic energy conversion like I would use coal or any other fossil fuel. Okay. So let me finish up by asking you a question. In your mind, what's the most important discovery of the 20th century? Any answers? Car. What else? Transistor. What else? Electricity. What else? Atomic energy. What else? Internet. Yes. I think all of them are fantastic discoveries. But there's a very important discovery, and I'm going to give you the answer in just a second. All of them were great. But could we, as humanity, have lived without all of this? The answer is absolutely yes. There's one thing that we can't have lived, and this happened in the early parts of the century. And this was way back in 1898. That's the beginning part of the previous 100 years. This is Sir William Crookes, who was the president of the British Academy of Science, kind of equivalent to our National Academy of Science. He basically launched a kind of a call for all scientists to solve an important problem. Nothing to do with any of the things that we talked about. It had to do with food. Okay? What was happening in Europe is that the population was growing very fast. Nitrogen in the soil was depleting. And the bacteria and the biocatalysts were not sufficient to replenish the nitrogen. And so the output of crops in Europe was coming down quite a bit. Okay? That call was heard all through, and of course we all know what happened. Basically in the early 1908, Fritz Haber, a German chemist, discovered a process by which catalysis could be used to make ammonia, which is a very, very critical step in forming fertilizers. Okay? And in 1913, an engineer. And this is really the big message that we want to take away. You want people with different competencies, complementary competencies, working together to solve a very big problem. So Karl Bosch, who was the founder of BASF, he developed the mass process to make fertilizers. And we know that this basically solved not only Europe's problems, but in the 60s, the Green Revolution happened. India, China, name it, everybody developed based on the discovery of fertilizers.
Yes, China has a dead area because of using too much fertilizer and the dead zones in the ocean. So we have to look holistically as a whole.
Fantastic point. Absolutely. What a wonderful point. I completely agree with you. Now, discovery of fertilizer doesn't automatically mean that one can put fertilizer everywhere and for every reason. So, moderation is a very important component. You make a very, very interesting point. But the key point is that there is a first step in all of this, which is triggering the need for food, which all of these discoveries solve. Okay, so that basically brings me to the last view graph that I have. Energy today is as big a problem, or energy in the environment. Energy doesn't go away from environment. As big a problem that you can think of in the past 100, 200 years. Every decade, every millennium has its own set of problems that human beings had to solve. By far, this is a fantastic problem that we all collectively need to work together. We need to have the science and the technology. A place like the Berkeley Labs can really address all of this within the energy framework. We need to exploit the basic science, what we learn from the science, and to create new technologies. Silicon Valley, the Bay Area, is just a fantastic playground. The ecosystem here is just fantastic. We also need to work with the folks who implement policy. Energy is very, very closely intertwined with policy. Of course, we need partnerships. We need partnership between national labs, universities, industry, international. We should not forget that energy is a global problem. India and China are very, very key players. That gives me a very good point to segue into Nan, who is going to talk about the international component of this.
So, Nan, why don't you join us? So I'm curious, for those out there, if those who are renting, would you be willing to pay 10% more to have solar installed and 10% more rent in a solar building? Raise your hands. Those of you. Okay, how about people who own their homes? Would they be willing to pay 10%, 20% more in a tax of some sort to have solar installed? No? Yes?
Would it decrease our electricity bill?
Okay, all great questions. See, you can priming you for later. And so how about your tax dollars at work for scientists like Ramesh, right? Does that seem like a good idea? Yes, okay, I agree. Okay. Nan, take it away.
Good evening. My name is Nan Zhou. I work for China Energy Group at LBL. And tonight I will be talking about China's energy efficiency policy measures and what we're doing and to help China to improve the energy efficiency. And first of all, a brief introduction of our group. And our group was founded in 1988. And we're probably one of the first group and outside of China and focused on energy efficiency and policy. And probably we're also remain one of the strongest influence in China. And what we're our area of research, mostly we'll try to look at what international energy best practice policy is and try to apply those to China. And our area includes appliance energy efficiency. And this is, here is a, I wonder if it's a label for the China appliance energy efficiency and then standards. And another area is building codes. And we helped China to develop building codes. And through our collaboration with China and using our simulation model and methodology to help China to and develop those building codes. And also we work with China on the industrial energy efficiency to help their plants to become more efficient and also introduce the international best practice and both in terms of the policy and the technology. And we also do modeling, and we look at China's energy consumption, current situation, and then we project the future energy consumption, and also looking at the policy impacts and of the different options. And other than that, we also evaluate the effectiveness of this policy to see if this policy were successful and effective in terms of reducing energy consumption and reduce carbon emission as well. And our model of collaborations mostly through bringing international best practice to China. Currently, we have more than 40 projects in China. And we collaborated with about more than 50 institutions in China. And also, we bring in a lot of Chinese counterparts and to the lab and get them trained in terms of methodology and then to get them to get used to the policies, measures, and technologies developed at our lab. So next slide is about the primary energy consumption in both China and the US. And on the right-hand side is the US energy consumption by sector. On the left-hand side is China. So if you compare these two, and we can see that China's energy consumption is still smaller compared with US. And however, it's been increasing very fast in the last 5 to 7 years. So, but the energy consumption in the US hasn't changed that much in the last few years. And secondly, from this chart, we can tell that, that in the right-hand side, the energy consumption in the US, the red and the green is building energy consumption, and blue is transportation energy consumption. And you can see from this chart, in the US, most of energy is used in consumption and driving, people driving and moving goods, and use electricity in their household. And however, if you look at the same figure in the Chinese energy consumption chart, you can see that the red and green part is very small and only accounts for about 20% of the total, whereas in the US, it accounts for 40%. And transportation accounts for 30% of the total energy. And there's a large gray part in China's energy consumption mix, which is industry. That accounts for about 70% of the total. And if you compare that with the US, that part is only less than 30%. So industry in China's energy consumption is very important. That's why we paid a lot of attention to bringing the industrial energy efficiency measures and technologies to China. And another point we can make is that, Chinese people, they're still using much less energy in per capita compared with the US, and particularly in the building sector. And if China in the future will use as much as energy as the Americans are using, so the impact on the world energy consumption, energy security will be very big. That's why we focus on China. And among this energy consumption, most of the source is from coal. It's about 70% of the energy used in China is coal. And so if we look at what that implies, and in terms of the carbon emission, which is the next slide, and we can see that in terms of the similar chart, but this is energy, this is carbon emission. And we can see that China's carbon emission has already surpassed the US to become the world's largest. And also it's been increasing very much in the last few years. Therefore, to address the climate change issue, and China and the US are the key players, and that's why we have to work together to reduce the energy consumption and reduce the carbon emission. Why has China's energy consumption grown so fast in the last few years? And we probably we all understand that in the US, and most of the population already live in cities, so about 80% of the people living in the city. And however, in China, this figure is only 50%, less than 50%. And in the future, they will continue to be urbanized. So there will be more people living in the city area. So we, based on the UN projection, and there will be 375 million people and moving into cities by 2025, between now and 2025. This is the equivalent to the entire US population. So we're talking about urbanizing the entire US. So once all these people start living in the city, and they will need buildings, and they will need steel and cement to build the buildings. And that's why in the last few years, the steel production, the cement production, has increased a lot. So if you look at this chart on the top, and two charts on the top right, and one is steel production, another is cement. And for steel, it quadrupled. The production quadrupled in the last 7 or 10 years, and for cement, it's more than doubled. And basically, China is producing half of the world's total production on both cement and iron steel. And once all these people started living in the buildings in city, and they will start buying, purchasing appliances, and they will use water, and they will consume goods. So if we look at the next chart, which is on the bottom, on the right-hand side, and this is basically ownership of the major appliances in China, and how they've grown from 0% to close to 100%, and for most of the appliances. So in the 1980s, a lot of the households didn't have any appliance. And in my family, we had the first TV in 1981. And we're one of the first family who had a TV because my uncle worked in the TV manufacturer. So he got all the parts and assembled the first TV. So every night, we have the whole courtyard, about 18 families, coming to my house and bringing their own little chair and just sitting there watching TV together. And about 20 people, they're all packed. And however, if you look at what happened today in 2006-07, and most of the households already have clothes washer, refrigerator, air conditioner, TVs, and some of them started having cars. And so with China's continue to get urbanized, and getting the energy consumption low and keeping the emissions down will be very challenging for China. We already saw in the early chart that China produced more than half of the world cement, and also steel. And cement uses a lot. Making cement uses a lot of energy, and that's why. And we particularly targeted the cement industry in China. And what we have done to help the cement industry to become more efficient includes policy, bringing the best practice policy to China and developing tools. And for example, we developed this benchmarking tool for the cement industry in China. In this tool, a cement plant can compare their energy consumption level and with the world best practice, and to see where the gap is and where the potential is. And based on the comparison, they can identify the areas where they can improve. And we provide a menu that includes more than 50 energy-efficient technology and the measures. And the plant can play around with all these measures and technologies and choose what's applicable for their plant. And they can look at the description of the technology, and they can look at typical energy savings, and also look at the cost, benefit, and the payback period. So the two charts on the bottom shows before, and they implement some energy-efficient technology, and after they implement some technologies. And you can see their energy consumption score in the first chart on the left, and it was 156, which is 146, which is 46% above the world best practice level. But after implementing all these technologies, their score went down to 114. And so it's only 14% above the world best practice. We don't just do some research and write a report. And we also do a lot of groundwork in China. And in the past 2 years, we provided a lot of training to our Chinese counterparts and industrial associations and cement plants using this tool. And last year alone, we trained about 300 staff from more than 200 cement plants. And also this year, we're planning to train about 42 cement plants and their employees and to use this tool. And one uniqueness of the work we're doing is that we don't just fly in China and make presentations and leave. And we also conduct all these trainings and work very closely with our counterparts in China. Sometimes we bring them to the lab to work from 6 months to 2 years. And also sometimes we go to China, we stay there for 1 month, 2 months, and just to work with them very closely. And you can see some photos where we're working. And to have some impact, and we really need to understand some of the policy and the cultures and in the local area. For example, and my colleague Lynn Price, who's sitting in the audience, and I went to a lot of cement plants to provide the training. But in some of the provinces, they have very heavy drinking culture. So they will force us to do bottoms up. And they have different cultures in different areas. So I don't mean that we just play like a drink all the time. But that's some type of culture we need to understand. And another example in helping China to improve the energy efficiency is in building areas. I just talked a little about the appliance ownership has increased from 0% to 100%. China only spent 30 years to achieve such growth from 0% to 100%, and which took US 100 years to achieve the same ownership. So if we can go to China and have early intervention in the form of the minimum standard and the labeling program, that would deliver very significant savings. And in the U.S., as we all know, that we have developed very strong programs called Energy Star, and I think you all see them on your computers, refrigerator, air conditioners. And so we introduced this Energy Star program to our Chinese counterparts, and we brought them to the lab and trained them to use some analytical tools we use to set up the standards. So they stayed in the lab 6 months or a year to learn the methodology, not just the solution. And so in the end, they can pretty much build their capacity and conduct all the independent research and develop a standard all by themselves. So now today, and they have about standards for 30 products, and then voluntary labeling program for 40 products, and mandatory labeling about 19 products to date. And there's a symbol on the left hand side, which is the information label. And you can see that there's different class. It's called Class 1, Class 2. And Class 1 is most efficient, and Class 5 is least efficient. And above Class 2, which is Class 1 and 2, is equivalent to the Energy Star energy efficiency level. So again, we do a lot of underground work, and we provide a lot of training to our counterparts. After we introduced all these policies and measures developed or implemented in the US and the developed world, and we also need to evaluate the effectiveness and whether they've been successful, whether they have saved any energy. So in terms of this appliance standard and labeling program, and we did impact analysis to look at how much energy being saved. So we can see from the chart that by 2020, and the electricity consumption can be saved by 11%, and just by implementing this appliance standard labeling program. And this figure in the US is 13%. So the Energy Star has been started in the 70s, and it took the US 30 years to achieve the 30% of the electricity reduction. However, in China, even though they started late, and they're catching up with what's being achieved in the US. And that's what will be saved is equivalent to about 28 gigawatts can be avoided in terms of power plant investment. And however, again, given the increase of the urban population, there will still be millions of appliances being purchased. Therefore, and introducing and continue to develop and revising the standard and the labeling program will be very important for China to achieve the energy efficiency. So last slide, I would like to show you some of the results from all these policies put in place by the Chinese government. And this line basically shows energy use per dollar GDP produced. And you can see that from 1980 to about 2002. And China has achieved a decline and decrease of this energy intensity, energy use for producing $1. And that's because during those 20 years, China had very strong energy efficiency programs, had ministries who's in charge of energy efficiency and energy quota and various measures, and to keep the energy consumption low. And basically, they achieved their target by quadrupling GDP with only doubling energy. However, the situation has changed since 2002. And you can see from the same chart, this intensity has gone up, and by 5% a year, and in those 4 or 5 years. And that's because of the opening markets and joining WTO, with China becoming the world factory. And also a lot of the energy efficiency program got abandoned, and the ministry was dismantled. So as a result, the energy intensity has gone up, and the Chinese government realized this is not sustainable. So they have to do something. And in 2006, they announced this massive target to reduce the energy intensity by 20% by 2010. So that's basically reducing 20% in 5 years. And we already saw that in the early years, China achieved the decrease of energy intensity. But at the time, and in the beginning, they started at a very low level. There wasn't any appliance standard. There wasn't a building codes. So it was relatively easy for them to achieve such goal. However, after 2006, and a lot of the low-hanging fruits has already been captured. So it became much more challenging for China to reduce the energy intensity. And however, and with a list of policies Chinese government put and implemented, and they have been able to put this put this energy intensity back on track. As you can see from the chart, it decreased annually around 4% and until 2009. And what we just learned a month ago that they are not doing very well last year because of a world financial crisis. And so we can tell they're struggling a lot to meet the target. And so, there's a list of the policies and Chinese government implemented to achieve target. And if you're interested, we can elaborate a little bit later. That includes the efficiency policies for buildings, appliances, and also for industries, and as well as power plant renewables and also the investment. So even though this is very challenging for China and to achieve all these targets and then keep the carbon emission low, and but if we hope to bring this carbon emission down and get it under control, China has to do it. With that, I will close my presentation. Thank you.
So I think this is a great untold story, but so I'm curious, has anyone heard of the China Energy Project other than those who are here who actually work in it? Raise your hands. Have you heard of it before? Just a few. Okay. I recommend the latest issue of Wired magazine. It's a story with Steve Chu, our former director, talking about the importance of partnership with China in reducing greenhouse gas emissions. It's a great story. Next up is Kurt.
All right, so I'm going to talk about another way to say no to carbon emissions, and that is the approach of geologic carbon sequestration. I'll describe what it is, how it works, why we need it, and some of the potential impacts that it may have. So the motivation for this approach is shown here in this sort of stripped-down schematic of the global carbon cycle. What we see here are fossil fuel combustion producing carbon emissions in the form of carbon dioxide. And this is occurring at a rate that's much faster than either terrestrial ecosystems or the oceans can take up. So we have photosynthesis going on, we have uptake in the soils, but it cannot keep up with the rate that we're putting it into the atmosphere. Similarly, in the ocean, it's taking it up, the pH is going down, but not at a rate great enough to keep concentrations in the atmosphere stable. So these are going up, CO2 concentration going up. This is causing greenhouse effect, which leads to global warming and the associated climate change. So the idea for geologic carbon sequestration is to just cut off these emissions right here from point sources, take that carbon dioxide and inject it deep underground where it will stay indefinitely. Looking at this in a little more detail, we see here a point source of CO2, such as a coal-fired power plant. I'll just show here the whole chain of processes involved in this. We need to capture the CO2 from the flue gases coming off of this power plant. So this is a step that needs to be done. Once we've captured the CO2, we'll need to compress it to put it in a liquid-like form that makes it efficient to transport. That transport would be done by pipeline where necessary. We would transport it, sometimes great distances, to places that are very nice and well capable of taking the CO2 through injection and storing it deep underground. So I'll focus now on this step here. So what's shown here is a real schematic cross-section of a sedimentary system somewhere in the Earth's crust. We have an offshore section and an onshore section. These areas exist throughout the world, not everywhere, but in many places. What's important to remember for the crust of the Earth is that there are not large caverns or large void space. The fluids, the water, the oil, the gas, the things we know about that are in the crust of the Earth are actually in the pore space. So most of it is grains cemented together with pore space. So what's shown here, for example, a familiar sort of an offshore platform, and we know there may be oil or gas trapped in sedimentary formations, and that stuff can be produced. Those are fluids that are basically, they've been sequestered there for geologic time. So the idea for geologic carbon sequestration is to kind of do the reverse of our extraction of hydrocarbons. We want to put that CO2 back. So illustrated here are several different scenarios. Let's just look at this number one here first. This is an injection of CO2. You see this nice structure here to take it. The darker brown rock here would be a low permeability rock like a shale. And the rock that it's being injected into would be a higher permeability, higher porosity rock like a sandstone. So the CO2 comes in, is injected, and then it stays there because it cannot rise up through that lower permeability rock. Note that the depths here are quite large. This is more than 1 kilometer. This is because, again, we want to store CO2 at depths where it's actually in a liquid-like form and it's actually quite dense. So how big a role can carbon capture and storage play? This is a figure actually you had as a handout, and what we're seeing here are our emissions from fossil fuel use of carbon dioxide globally. We emit globally about 30 gigatons of CO2, so we're somewhere here in 2010. It's possible this has gone down just a bit with the global recession, but we're somewhere in the range of 26 to 30 billion tons of CO2. If we keep on a path, as we've been doing in terms of growth of population, manufacturing, etc., we would increase our emissions along a curve like you're seeing here. And it would put us out in 100 years or so at about 80 billion tons of CO2 per year. So concentrations in the atmosphere would rise a lot. What we want to do, what LBL and other people concerned about this are trying to do, is to take away those expected emissions. So that's represented by this shape here that I'm describing. If we can find a way to not emit along this curve, but instead to emit along this curve, we can reduce our emissions relative to the business as usual and maybe keep global warming to something along the lines of 2 degrees C or so. If we keep going like this, we'd be up 4 degrees C or maybe more. These are very uncertain numbers. So how do we do this? People recognize that there's no one answer to this problem. It's a huge, huge problem, but they can envision piecing together various solutions. So here you're seeing conservation and energy efficiency. That's something that we can do to account or displace this much of the expected emissions. Similarly with renewables like solar energy and wind, if we can grow that as a fraction of the energy that we use, we will not have equivalent carbon emissions. And onward, if we can switch and start using more natural gas, which is a lot cleaner than coal, we can increase that contribution and not emit that carbon. And finally, you'll see this huge role here projected for CCS. So some people think CCS can be really one of the most important components of avoiding this emissions wedge. So this is shown here, just rough numbers of ramping up from something like a gigaton per year, which maybe we could be doing in 15 or 20 years, ramping that all the way up to 15 gigatons per year, say in 90 years or so. These are big numbers. What do these things look like? All right, so here's the city of Berkeley. This is a cubic kilometer box here that I've just sketched onto that. If this box, just as it was filled with water, this would weigh 1 gigaton. So remember, Earth's CO2 emissions are about 30 gigatons of CO2 per year. If we took carbon dioxide at those liquid-like conditions that I'm telling you exist deep in the Earth, it would be maybe 30% larger a volume than this. So a gigaton of CO2, just in its liquid-like reservoir form, might be 30 to 40% larger than this. Now, bear in mind what I said about porosity. This fluid is occupying only the pores of the rock, so in fact it would occupy a considerably larger volume. But this gives you some idea for the magnitude of these emissions. So what makes us think that the CO2 is going to stay there? Well, shown here is the figure I'll point you to, which is a very classic figure showing the trapping of natural gas or methane and oil and water. So oil and gas and water here have stratified themselves based on their density. These are light fluids. They float up over geologic time, again, through the pores of the rock and accumulated up against this shale cap rock, this low permeability rock. So this is a storage phenomenon that Mother Nature played out. These fluids are there in a reservoir form. We drill wells into them and produce them. This is exactly what can be mimicked for carbon dioxide. So the first order trapping mechanism is the simple one that you see here. It's called structural trapping, and it's analogous to the way oil and gas are trapped naturally in the Earth. Now there's another very fundamental trapping mechanism, and that's the second one. It arises when CO2 and water are moving through the rock. For example, the CO2 rising buoyantly and water coming in behind it. Small blobs, little bubbles of the carbon dioxide, even in this liquid form, get trapped as this flow process occurs. And it's sort of like when you have a sponge and it's filled with water and you let it drain. That sponge isn't dry. You really have to squeeze it to get the last bit of water, and even then it's not dry. So this is the residual CO2 that stays behind during a flow process. What this means is that you don't even need to have a closed structure to trap CO2. If some small amount of CO2 were injected here and simply allowed to migrate through the pores here, it would actually all become trapped after migrating some distance. So this is the second trapping mechanism. A third one, very fundamental, is simply dissolution. So the CO2 will dissolve into the brine at depth, just like a carbonated drink. And in fact, when that happens, the water, the brine, becomes even denser than it was before, so it occupies less volume and tends to stay down. So we've got structural trapping, we've got residual gas trapping, and we have solubility trapping. The final one is really the holy grail, the most stable form of trapping, is if this CO2 would react with minerals, react with components in the brine, and create a carbonate mineral. So we know this does occur, but it occurs very slowly. So there's research going on at LBL to speed up this sort of reaction to make carbonate minerals, to make a very stable form of geologic carbon sequestration. So where can CCS be carried out? Well, I haven't shown you the sources here, but you can imagine there's a lot of coal-fired power plants throughout the eastern part of the U.S. and some in Arizona and New Mexico. Out here in California, it's mostly natural gas. So those are the sources. The sinks, though, I've shown here in blue. These are sedimentary basins in the United States. These are typically where we have oil and gas, which is shown in the red, by the way. So oil and gas producing regions tend to overlap with these sedimentary basins that are very nice places that CO2 can be injected. So this is the U.S. snapshot of where carbon sequestration could occur. Note that it's not anywhere. It's not in volcanic regions. It's not in the Sierra. It's not in granite, etc. So there are very specific places. Now there's plenty of geologic carbon sequestration going on now. There's an offshore project in Norway called the Sleipner Project, which has been injecting about 1 million tons of CO2 per year since 1996. There's a very similar project in Algeria that's injecting just about the same amount since 2004. The source of their CO2 is natural gas. So it's a natural gas source that's too high in CO2 to sell to the public, so they strip the CO2 and re-inject it into rocks nearby the reservoir. Okay, so we've talked about what it is and how it works. I'd like to talk now about some of the impacts. What's going to be the effect of doing this? So sketched here is just a schematic of the depth and then something about the health, safety, or environmental impact, just all very qualitative. So recall, we're going to be injecting CO2 if we do this at great depth, and these are some of the impacts, some of the things that could occur. I'll start actually at the top here. So on this scale, these would be the most serious health, safety, and environmental impacts. So just about the worst thing that could happen is if somehow there were a horrible leak and CO2 came up from where you injected it and got right up into the ground, above the ground. CO2 is a dense gas and it flowed over the ground surface. This would be a very, very serious health and safety issue. Similarly, if it were to seep into your house or into your basement, again through a pathway that no one knew about, accumulating in a topographic low, all of these could have impacts on animals and humans right at the ground surface. Now, we typically cannot find any route, any path for these events to occur. So moving down, we have things that are happening in the shallow soil. It could affect the roots of plants and trees. Again, if there was some sort of pathway that we didn't know about. The vadose zone is the area right above the water table. This could also be impacted. Probably the most serious regions or potential impacts that are of concern are CO2 leakage from depth up into potable groundwater aquifers. So this would be a water resource potentially contaminated by CO2. It's not so much the CO2 itself. We know we can drink Perrier and Calistoga, but it's what that semi-acidic water would do to surrounding minerals in terms of bringing components in. It might degrade the water quality. The second most interesting impact of concern recently is this question of induced seismicity. So when you inject fluids in the ground, you do create what's called microseismicity, earthquakes that cannot be felt in the region of the injection zone. And this has caused a lot of concern, and we're doing a lot of research on it right now, whether some of those earthquakes could be actually big enough to be felt and could lead to any damage. So these are really the two main impacts that are of concern today. Again, there's no pathway that people can see that's reasonable to allow these more serious ones to occur. So given those impacts, why are we considering doing this? Why might this be a say no to carbon emissions strategy? Well, what's plotted here from the IPCC is, again, impact here on this axis in several different categories. And right now, the global atmospheric temperature has risen by about 0.8 degrees C. So we're somewhere right in here due to our excess CO2 emissions. And we can see now the impacts on food, the potential for rising yields in high latitude regions. They're seeing this, longer growing season in some places. But if we keep going, again, on that curve toward 2 or 4 degrees, there could be drastically falling yields in many areas, particularly developing countries. With respect to water, it says here small mountain glaciers disappear. Water supplies threatened in several areas. We're seeing this in South America and Peru, where they rely on glacial water sources. But again, if we go further up this chain, you could have just significant problems with droughts, et cetera. And onward to ecosystems, this says extensive damage to coral reefs. We're seeing the bleaching, the pH of the ocean. It's definitely changing and affecting the ecosystems. So all of this figure is to say that there's strong motivation to do something about our fossil fuel CO2 emissions. And geologic carbon sequestration is one approach that we're doing research on to test its effectiveness and feasibility. Thanks very much.
So if we could have the lights up, the scientists will now take their seats on the stage and we will begin the Q&A. So I'm going to, my colleague is going to help on this side and I'm going to go over here. So give us just 1 second for the switch out. We on now? Okay. All right. So I'm curious to ask a question of the audience first before we get started. So you just heard Kurt's discussion of carbon storage, in which he mentions induced seismicity. So I'm going to ask the audience if you think it's worth the risk to make these huge gains in carbon in storage with the balancing that against the possibility of small earthquake, let's say an earthquake of 2.5. How many people would say that's okay? Okay, how about 3? 3.5? Do I see 4? Okay. All right. Okay, who has the first question in the audience? Okay, one right here.
This is.
Please identify yourself.
I'm Mark Wagner. This is probably a question for Dr. Oldenburg, although any of you might be able to answer it. Is there any concern with the amount of oxygen that we are taking out of the atmosphere, in particular with permanently removing the oxygen with sequestration? Do you want to touch that?
It's the CO2 sequestration question.
It's getting funneled to me. Not that I've ever heard of.
That's an interesting question, though. Will you actually?
Well, I don't know if you do the calculations, calculating the amount of gigatons of carbon dioxide that are produced, and for every molecule of carbon dioxide, you have 2 atoms of oxygen. I don't know. I haven't done the math, but it seems like it might be something that someone should have thought of.
Okay, Dan, why don't you?
Reverend Earl Coteen, Unitarian Universalist Minister, Berkeley Fellowship. Tonight I could have been listening to Bill McKibben on the radio saying that he believes we've already passed the tipping point. Do you share his fear? And if so, what is your enterprise going to do to try to awaken politicians to the real dangers we're facing now?
I can take it if you want.
I'll add to it after.
Okay, yeah. So I guess that's a very interesting question. My own impression is that that's almost like religion. Everybody has a take on whether you're on the left side of the critical point, you're at the critical point, or you're way past the critical point. By far, I think the best thing that happened is somebody like Steve Chu going to Washington, because he's a guy who has been, I would say, the chief priest in this whole process of proselytizing all of us in terms of thinking about this problem. And the fact that he's in a position where he can actually enact some of the things that we worry about is, I think, a fantastic thing. I believe, I'm not a political person myself, I don't have any left or right leanings, but I believe there's a huge amount of sensitivity worldwide to the issue. India, I just came back from India. I'm sure Nan will tell you that China is equally sensitive. So to me, it actually doesn't matter whether you are subcritical or supercritical. The fact that we're assuming that we're going to be critical is the most important thing, and acting on it. So we could always toss a coin, but I think it's better to put the coin away.
Yeah, I would agree with that, and second, that we do have an energy climate crisis, regardless of just how far along we are. Right. And maybe to the second point, what are we doing? What's the lab doing? Yeah. The Carbon Cycle 2.0 is a front-center initiative headed in that direction. Right. And I think it really is important that everybody understand just how serious this issue appears to be. It's, as you all know, it's a really difficult one for people to get a handle on because the changes are slow and people aren't seeing things. I'm a geologist, so from that perspective, this is just lightning fast, and it's very, very serious and very alarming. So we need to be concerned.
I promised my friend Francois up here that I would allow him to ask a question early. He's right here.
Thank you.
My name is Francois, as he just told you, and I want to know what percentage of the world's energy is renewable, and when will, and if solar cheap will ever be dirt cheap, and when exactly?
So, dude, if you look at my chart, my Tokyo subway chart, very small fraction. It's really small fraction of our energy usage is from renewable sources. Okay. So, in terms of the second question that you asked about when is it really going to be dirt cheap, I guess I should have qualified what I mean by dirt. Dirt in some places can be quite expensive depending on what the dirt has. So dirt cheap always has a reference point, and that reference point is fossil fuel. What is the cost of fossil fuel? Typically, depending on where you are in the world, it may be a little bit different, but typically that's about 5 cents a kilowatt hour if you're going to use coal or petroleum. So everybody benchmarks to that number. So if I can meet 5 cents per kilowatt hour within an error bar of 10–20%, then solar will become very pervasive. Now, a lot of people, if you're an optimist, you say, oh, it's going to happen by 2020. That depends on several factors. Of course, the cost of solar is still about 30 cents a kilowatt hour. So we have to come down by about 5–6 times. There are people who will say, look, put a carbon tax. If you put a cigarette tax, you can put a carbon tax on fossil fuel. So you kind of balance out these things. But we're still not there yet. If I were to, I have to be optimistic, and I think as scientists we generally tend to be optimistic. I would say in about 15 years, there's a good chance that we could catch up. And depending on the policy, it could happen faster. That's a very good question.
Hi. Can you hear me? Oh, I was wondering if anybody's actually taken the lab's advice on using malachite and started trying to develop something from that in the private sector?
Malachite, you mean? So this is still in the research stages, and part of our portfolio is to explore questions that nobody's ever thought about. And so we do have patent portfolios on this. We're just beginning to build up. We're just in the process of doing a startup-based company on this idea. It's still not where I can start delivering panels to you based on malachite. It's still in the research stages. But having said that, I tend to be very optimistic because many of these experiments, if they have to work, they work the first time. And then you start improving on this. And that's essentially what happened. The first experiments worked. So for sure, the next 6 months will be pretty exciting for us in terms of commercializing it. There's just a lot of different steps that have to go on. How do you actually put it in a platform that will start to generate large area panels and stuff like that. But definitely we're pursuing that. By the way, it's not just malachite. You could think of other sources. Cuprite is another source. The sulfides of copper and iron are also very good candidates. They're very available throughout the world.
Okay, we have a question over here.
Hi, my name's Glenn Wolkenfeld. I'm a teacher in the Sustainable Energy Program that we're setting up at Berkeley High School. And my question is, if we were to take carbon from a coal-powered plant and sequester it, what would that do to the cost of coal-powered electricity, and would that make technologies like wind power competitive with coal?
Yeah, the costs are considerable. I didn't get into that, but one way of thinking of them is what we call the energy penalty, which is the additional amount of energy we'd have to use to carry out carbon capture and storage. And that number is anywhere between 10 and 40%. And so 30% might be a good number. With respect to a cost, Jeff asked a question earlier about cost. The price of your electricity might be expected to go up by about 50% in a CCS sort of scenario. And so, yeah, if you had those additional costs, again, brought on by policy, renewables and other sources would certainly become competitive.
So does the audience think that's acceptable, to have pay 50% more for electricity? Yes? No? No? Okay. All right.
We have a question over here.
Yeah. Shelby Solomon. I'm actually very shocked at this chart. Right, it goes out to 2095. And given the 20 to 30 years to figure out solar and get the cost down, right? Power plants last maybe 50 years. So by the time you get out to 2095, renewables should be a huge chunk of this, right? We ought to be off of coal and gas entirely.
We hope so. Yes, indeed.
So I guess I don't understand this chart unless you're really pessimistic about what's going to happen in the political environment.
It's one model. You see that little mini-cam word? It's one sort of scenario. And And I agree with you. The future is very hard to predict, but that's one way of looking at a scenario.
Okay, we have a question here.
Hi, my question is for Kurt Oldenburg. You gave a kind of a description of what global warming is, and basically that we're in such a desperate situation that we need to rely on these kinds of things. And it reminds me of Ken Caldeira going to Congress and saying that we need to do hazing of the sun and to mitigate global warming, or to use solar radiation management is what it's called.
Mm-hmm.
And if you Google upper atmospheric releases, you will find that the U.S. military and scientists have been involved in this for decades. In fact, even in 1950s, they've been using ionospheric heaters to heat up the ionosphere. They've been spraying metal aerosols on a daily basis. Hundreds of planes go out and spray these aerosols into our atmosphere and use our atmosphere as a physics laboratory. If you think this is not a factor in global warming, I don't see how you can think it's not. And I guess my question is, I mean, I related it to your talk because you're talking about, well, here are the risks if we don't do anything. And I have to say that I don't really trust scientists. I think scientists have gotten us into this.
Okay, panel of scientists.
The last part I couldn't hear very well. Can you see? No, I'm serious. I couldn't really hear. Jeff, can you repeat what you said, the last part?
I will let her repeat it.
Yeah, please. I couldn't hear.
I feel that scientists have actually created global warming with this atmospheric heating, with spraying of aerosols, creating man-made cloud cover. Even NASA says it creates warming of the Earth. And NASA is been involved heavily in these experiments. By the way, solar is going to be affected by solar radiation management because it's going to be screening the sun.
You bring up a very disturbing question. It's a very important question. So the way to address this, and I'm sure Kurt probably has a better numerical feel for it, is what fraction. Let's say the folks went out into the upper atmospheres and started doing this aerosol type experiments. And the question is what fraction of that contributes to the greenhouse effect. And so if that fraction is significant, when you say, oh, you know what, these scientists need to be put behind bars or need to go to different bars maybe, you know. But my impression is, this is again just a gut feel, my impression is that that's a really small fraction of the CO2 that's coming out.
Every day, over my house, I see the clouds spread out, the line become clouds.
Right. So one should not deny this. This is an observation. Definitely, it's documented. But I think it is. My impression is, again, Kurt, maybe you have a better feel for the numbers of this. Impression is that the CO2 that's being generated from the oxidation of fossil fuels would be a significant fraction. You know. And therefore, in principle, we have to address both of them. I completely agree with you. I think in principle, we have to address us as a group. Do we need to do these kinds of experiments or these kinds of studies, which increases the chance of a greenhouse effect? I think that's a very...
You're experimenting in our atmosphere. Scientists are experimenting with using our atmosphere. And you seem to think you can just insert carbon dioxide because we, idiots, regular population folks...
I'm going to suggest that we continue this conversation after the... at the conclusion, so we can get to more questions. Dan, you have some
We have
more?
another question right here.
Hi, my name is Chris Rajkowski. Hello?
Yeah.
My name is Chris Rajkowski. Maybe drifting away from the interesting science questions, ultimately this is a human problem. It's created by humans, so maybe we can think a little bit about that for a moment. There's probably two countries to focus on in this little discussion. One is the U.S., one is China. So
And
maybe shifting over to the political side, I can ask Dr. Zhou. We hear a lot of discussion about the developments in China on the political side and new policies put in place. Maybe some of your thoughts and opinions on just how meaningful are these policies that are being put into place in China? Is it just propaganda, or is it actually something meaningful on the world stage in contributing to energy, shifts toward renewable energy and reduction in climate change greenhouse gases?
Yeah, so there are a lot of policies that I haven't had time to mention in my presentation. But as one example, and to support this 20% intensity reduction goal, which I just briefly mentioned in my presentation, and Chinese government launched this program called Top 1,000 Enterprise Program. And that's targeted most energy-consuming industries in China. And all these top 1,000 enterprises, they account for about 30% of total energy consumption in China. So the government basically gave them targets for them to reduce their energy consumption and by a certain amount in the 5 years. And the companies, they all signed agreement with the government and to promise they will achieve the goal. To achieve the goal, they had to implement a lot of technologies, policies, and they have to train people to conduct energy management, energy auditing, and which has been also dismantled for a long time. So they had to resume all these activities. And it's very serious target, and companies also took it very seriously. And we heard a lot of the executive of the companies and complaining or talking with us about their headache in terms of achieving this target. Some of them could not sleep at night just because they promised and they did not know whether they can meet it and how they can meet it. So they took it very seriously. And we look at the results, and for the first 3 or 4 years for this program, particular program, and we found that and a lot of them already surpassed their target. And most of them are meeting on the track to meet their target. Only few of the companies probably had a difficulty meeting. But overall, the program has been very successful. And this is just one example of the policies, list of policies Chinese government puts in place. And they also took very serious programs to close down the inefficient power plants, inefficient cement plants, and a lot of small factories. And so, and they closed, I forgot the number, maybe my colleague Lynn Price can remind me, but it's equivalent to, for the cement, probably equivalent to the entire US cement production. And for power sector, it's the same. They've closed down a lot of inefficient power plants. And also, in the last few years, they've only been putting in the supercritical, very efficient power plant. And in terms of renewables, and China also is very progressive in the renewable development. And they kept revising their goal and target and to increase the share of renewable target in their power portfolio, power sector portfolio. So their new goal is to install the capacity of 150 gigawatts and for wind energy by 2020. And they just recently announced this target, which is about 30 gigawatts more than they previously planned. So this year, China has already become the second largest wind turbine producer. And next year, they're projected to be the #1 wind turbine producer in the world. In terms of solar energy, and China is already the biggest producer for solar panels. And also, they recently revised their target for nuclear and to increase to 80 gigawatts by 2020. So all these suggest in a lot of these renewable and energy efficiency area, China is already catching up and probably is already leading. So if we in the U.S. don't accelerate our policies or the effort in this area, we'll be left behind.
I think the same thing can be said for India too, maybe a slightly lower level, but they just announced a huge solar emission program, created a new ministry for for energy and environment and stuff like that. So they have some very ambitious goals already put into place. And clearly, all of these are in places like India, it goes up and down with the political environment. But I think there's a lot of conviction that they do need to do something really substantial. Those are the two big animals, China and India, one really needs to tackle.
So there's a question over here, but I have one follow-up. So is it easier for China to do these things because of its style of government? Do they have an inherent advantage? They can just order it done?
I would say that China probably has the advantage to really implement the national goal, which is the mandatory goal, and also all these mandatory programs, and for the particular political system and in China. So they can basically ask the companies to agree on the absolute energy reduction, and also they can just announce and the goal and to ask all the sectors and industry to achieve those goals. So I would say China does benefit from the political system in terms of doing the energy efficiency.
Hi, I'm Emily Bartlett, a graduate student at UC Berkeley, and this is mostly directed at Professor Ramesh. You talked about price as being a big factor controlling solar and what it can do for us in terms of energy or renewable energy. But another factor to consider is how to integrate it into the grid or make it a major supplier of electricity. And so have you considered what you'd want to do about like storage or?
Fantastic point. So we didn't have time to, this is a really important point. The romantic part of this whole thing is, oh, you put solar cells, you can see God, everything is fine. No, I don't think that works that way. The real issue with photovoltaics or solar cell is not actually the solar. Of course, there is a key component of the cost of the solar panels themselves. The real issue is what happens when the sun turns its switch off and you're sitting there, how do you store all the energy? So any solar program has to go hand in hand with a very good quality energy storage. Right now we do it in a very crude fashion. That needs to get really much better in terms of storing the energy. Interfacing it to the grid is the other issue, of course. That's possibly a solvable issue because it can have smart grids and stuff. But the storage part of it is by far a very critical issue. So you bring up a very, very important point. By the way, just we haven't had a speaker from LBL, but by far some of the most cutting-edge research and development work on battery technologies is happening at LBL and on campus as well. And people are looking for low-cost approaches, chemically benign approaches for energy storage. You know, there are other new mechanisms of storage. All of these are very critical. Very good point.
Hi, I'm James George. I'm reporting with EnviroBeat. And I have a question that addresses two of the topics tonight. One is China's growth in energy, and the other is the carbon sequestration. Obviously, or maybe not obvious to everyone, but it looks like LBL has done great work working with China. And China is taking very strong steps, obviously. At the same time, China is growing so fast. And the first part of the question is, if the best case scenarios with China's efficiency measures and alternative energies are carried out as they're planned, still will China's emissions grow, and how much? And this has to do with China's dependence on coal, particularly, you know, James Hansen has said, if we don't phase out coal, we're toast, you know, as a planet. And I'm not at all bashing China, because I think China's taking stronger steps than the United States in many ways, despite Stephen Chu's great intentions. You know, the United States only proposed, I don't know what, 5%, no, it was 3% below 2004 levels at Copenhagen. Very weak targets for political reasons. So we're anticipating that China's going to continue to use coal, and a lot of it. The United States will continue to use coal, and a lot of it. Is this dream of carbon sequestration sort of an enabling dream? Is that possible, considering the 30% energy penalty? I mean, I was in China, I talked to people there about the coal use and the scrubbers just to clean up the coal. They said they often turn them off for the modest savings. And if you're going to tax basically a 30%, is it realistic to assume that people will really do this? So you can take it from there.
Did you want to start?
Yeah, I think you made a very good point. We recently just finished our preliminary we just finished this we call 2050 China's energy demand model, and we just had this first round of results. And we found that China's energy consumption by 2050 will not peak. So will continue to grow. And for the reasons you just mentioned, urbanization, and people will be continue to pursuing more comfort in their living standard, and they will continue to purchase stuff, buy cars, and use cars. And however, when we look at the carbon emission, and with all the renewable targets Chinese government has set up, and also with a list of this energy efficiency measures, China can reasonably keep the carbon emission not down, but at plateau, and keep it this leveling off like around 2030. So, and just by doing the energy efficiency and the renewable plus nuclear, China can actually make this the level kind of the growth slow down, and the level and kind of flat. However, if we want to have a peak in carbon emission to make the absolute emissions down, then I think the CCS carbon and CCS plus IGCC and some other decarbonization measures needs to be put in place in order to make it decline.
So with respect to the question of whether it's enabling or not, I think that there's some complex issues and complex factors that will play out. I mean, immediately we've talked about the energy penalty, the increased cost. So as soon as we're paying more, the other options become more attractive, and renewables can slip in. So I think it's actually kind of hard to predict just what will happen, if you adopt something like this. And my feeling is I don't view it as an all or nothing by any means. It's something that it seems viable. We have the issue today. It seems viable. We want to try this at larger scales than our pilots and demonstrations. And we're going to learn by doing as this goes on. And we may find that capacity, for whatever reason, is in fact smaller than some of those rosy projections are. But we have to get into this. We have to know. Again, back to earlier questions, it's a problem that's upon us right now. And I don't really advocate the idea of doing research and figuring out some supposed exact silver bullet solution and adopting it 15 years from now. I don't think that's realistic at all. We should be doing what we can, where we can, see what works, see what doesn't work, and the dynamics of all that may, again, if we're optimists, may play out in a very nice way and show some new technologies coming in that end up significantly reducing these emissions.
So we have another question over here, but I'm curious to know how many questions are there left in the audience so we can get some sense. Okay, I think we can finish off that round, and then we can close off the evening, and I'm sure the scientists will make themselves available for a few minutes if you have additional questions at the end. So we have one here.
Hi, I'm Hansen Su. I work at LBL. So I think, like looking at these questions, there are two major questions that I'd like to ask. One is, it seems that inertia is probably a large problem, because you can talk about trying to bring photovoltaics to parity, but I think a large part of the people who are not sympathetic are not here. And so it seems like the problem is, how can we come up with ideas that can produce solutions so that it's not sensitive to every election cycle and the politics and the technology? Do you have any ideas on how we can go about doing that?
Okay, so let's take the first question, which seems a little bit more definable. There are many different scenarios that people are looking at, and depending on which part of the spectrum you belong to, your predictions may be different. But clearly, if you have a carbon tax, that makes it a little bit more level. Right now, let's use the number of 30 cents a kilowatt hour as a cost. By far, the most important thing. Let me give you a preface. I grew up relatively dirt poor in India, and my grandma always used to use coal. And we could just go basically buy it for, you don't pay much for coal. You just use it. And we never thought about CO2 and everything. So if you go back to my grandmother or anybody in my village and say, guys, you should be using photovoltaic, they probably laugh you out of the building, Because for them, it's cost, that's the only thing that matters. For most people, 99% of people, cost is important. So if we fix the price at something like 30 cents a kilowatt hour for the photovoltaics right now, clearly we need to come down by at least 3 times. 10 cents is manageable. And so you break down the cost of the photovoltaics and say, what is it that leads to so much of a cost? And if you look at it, the material, silicon, making silicon, which is 95% of PVs use silicon. And silicon, it turns out you take sand, which is silicon dioxide, and you reduce it. That's a nasty business because you have to put a lot of energy in to actually reduce silicon dioxide to silicon. And so you're already paying an upfront penalty in terms of energy. Somebody has to put some carbon there to burn some stuff to reduce that process. So that is a problem. And the second issue is how much of that silicon is available. Not much, only 5,000 tons is available, are available. So that's the material side is an issue there. So if you can take care of that, the idea that I was proposing will address that. If you can do something with minerals where you don't do any serious processing, that's one pathway. About 40% of the cost, believe it or not, comes from somebody climbing up to the rooftop, putting a clip on, and that guy slips and falls, your insurance rate went up, or he breaks the glass panel, your yield on your solar panel is an issue. So 40% of the cost is installation and those kinds of things which are not really central to the solar panel. So you could think of a fabric like this, which you could peel off and put it on. And people are now beginning to think about it. Konarka is doing roll-to-roll plastic-based solar cells. Now these are only 5-6% efficient, unlike the silicon, which is 12% efficient. But you can replace it, you can put it back on as long as it's cost effective. And so there are many pathways that one can take to try to continuously reduce the cost. Now, what people have learned, we all have learned from the semiconductor business, which is not a bad business, which is a $250 billion business, is as you go through the manufacturing process, you learn more about how to make your system more efficient, not efficient, better quality. Your yields go up. The cost of making it comes down. Excuse me, which is why semiconductor memory devices are all commodity now. Before 2000, they were not commodity. They were $30 a megabyte. So your costs will keep coming down as you put more and more into play. People buy it and put it in. So the initial parts of it, which is where we are now, is a little bit of a tough learning cycle. But once it goes in and you can start to keep up the manufacturing, then you will see that the prices keep coming down. Now, of course, if you have other issues to deal with, carbon tax could be a way to offset maybe 30% of the cost. And so you start leveling out this playing field. And so I hope that gives you some flavor of many different approaches that you can take to keep on reducing the price of PV. Repeat your second question. I kind of forgotten it. I tend to take a lot more optimistic view of this issue. I'm sure, I don't know what you guys think, but cost is clearly a very big issue. One could say that cost is not the only issue, maybe yes, but cost is clearly the biggest driver. When a customer goes and buys a solar panel, the first thing that you ask is, how much is it going to cost me? How long will it take for me to recover my upfront investment? So cost is important. So if I'm able to bring my cost down, then you ask the question, do we have the infrastructure to solve this, like coal-fired plants and stuff like that? I believe that infrastructure is not fully in place now. I mean, we don't have the ability to make terawatts of power with solar cells. Clearly, doing that with silicon is a problem. I don't think we can do that with silicon, but there are pathways that one can take. Organics are a possibility. I think those things are evolving as we speak. Whether they will be there right away is just a good question. But I think there are pathways by which one could go at it at the terawatt type level, which is what we really want. But I do believe that if we don't solve the cost problem, this will never make it. Guaranteed. So cost is the issue that we should be attacking. I don't know what you guys think.
I would just
add that the cost problem can be solved on the other side too. And
Exactly.
the policies of the
Right.
price on carbon
Right.
and things. But it's very difficult to do that, as we're seeing even this week in the U.S., given our system.
Oh, I would add one thing. I don't think solar or wind can replace all coal, because given our current power grid structure and the reliability issue, in the current situation, I don't think you can add all the intermediates, meaning solar or wind, for more than 20% of the overall portfolio, the generation. Because more than that, you create a lot of uncertainty and unreliability issue for the grid. And so as for China, and by increasing the renewable energy and target, and they can replace some of the electricity consumption. And however, it cannot replace, for example, oil. And you can replace a little bit gasoline by introducing and a lot of electric vehicles. But you cannot run on electricity still for heavy trucks and the ships and the airplanes, all these, the freight. So in our also the projection for China, and we also assumed all these renewable energy and will increase the share, but coal will still exist, will still be used, and in the economy.
Okay, let's take a couple more. There's one on this side.
My name is Sally Lake. I'm from Contra Costa County. I'm very interested in what you said about China lowering its energy use per dollar of GDP. And I have several questions relating to that. One is, how does the U.S. compare? Is the U.S. use of energy per dollar of GDP going up or down or staying stable? I'm also curious if a country's financial sector is a sizable part of its GDP. Would that enable the country to have good statistics, because it's not so energy intensive as an industry, to make the country look, due to its financial sector growing, like it's getting better statistics in its energy use per dollar? And the final part, if you have enough time, is could you please explain if China is manufacturing a lot of goods which are then transported to the U.S., in which country, China or the U.S., which column will the energy cost of moving those goods fall?
Yes.
Can you remember all of that?
Yeah. I think for the last question, and we did a little bit analysis, and also we did a literature search. And we look at how much energy or carbon is embedded in the goods we consume, like that's exported from China to other countries. So I think it's most related to your question. And that figure is, for the exporting, it's about 40% of the total energy is used to just make all these goods and transport them and to the developed countries like US and EU or Japan. However, at the same time, China is also importing a lot of goods from all these countries, and also importing crude oil and other energy and from all these countries. And there's also embedded energy and emission, and that comes up at about 20-some%. So the net embedded energy or carbon in these goods is around 20%. And so basically, if we want to address all this energy consumption climate change issue, and we need to help China. and to lower its energy consumption in manufacturing and make their manufacturing more efficient. And so that the embedded energy consumption will be lower and lower. And for the first question, I think in the U.S., the energy per dollar and produced in the U.S. has been decreasing. And so in the U.S., efficiency has always been improving in the last 30 years, 40 years. And if I remember correctly, but the electricity consumption per capita has been increasing. And so basically, what that means is people, even though our buildings become more efficient, appliances become more efficient, cars become more efficient, but people are using more. People using more appliances. Now we have computers, TV, and all these equipment. We're adding more and more, and we're using more and more energy services. So per capita basis, at this per capita base, and it's been increasing. And also, however, at the same time, the electricity consumption per capita in California has been decreasing in the last 20 years. That's because California implemented a lot of very aggressive energy efficiency policy in the program, including DSM, the utility programs, and also very stringent appliance standard and the labeling programs. So that's why in California we can keep this figure, electricity consumption per capita, and going down. So that's what we also introduced to a lot of our Chinese counterparts and the government, and they were very interested in what California is doing, and they asked us to provide more information, experience on how California implemented all these policies, how they set up all these policies. And I'm not very clear about your second question.
Well, I think maybe we can, if you want to address that at the close, because we have to wrap this up. We have one last question for the evening.
My name is Bob Smith. I live here in Berkeley, and I'm retired. You mentioned several sequestration processes that were projects that were working now. Are any of those smokestack related? And if so, how are compressors and what have you to get it out? How do they get a gas out of a smokestack to carbon dioxide?
Yeah, so we refer to a CO2 captured from a power plant or some other man-made structure as an anthropogenic emission. So there are some anthropogenic projects, but now to your question, it's basically on the issue of capture. And so I didn't talk about capture. You notice it's CCS, carbon capture and storage, and I really focus on storage, so that's what I spoke about. But capture is a whole other area of research. When I mentioned the increased cost of carrying out CCS, 70 to 80% of that cost is actually in the capture part. So the standard method today are aqueous amine solutions, which are basically absorbents, and the gas is allowed to move up as these amines trickle down, and then in a stripping tower, temperatures and pressures are changed to desorb that CO2, and the amine is recycled back. So that's the standard way of post-combustion CO2 capture, and it's expensive, but it's very well-known technology.
So thank you, Berkeley Lab scientists. Thank you, audience, for coming, and we will see you in 2 weeks.